Now let's look at what are the objectives of today's lecture. We will be covering two things in this lecture. This is the start of chapter number 2 of your textbook. First of all, we will look at discrete time representation of some basic signal types. We are familiar with several signal types in continuous time domain. However, we will be looking at the discrete time representation of some of the signals you are already familiar with, such as impulse and step signal and exponential signals. But as I said, we will be looking at them from the discrete time representation. And the second thing we will cover today is to look at power and energy signals, and we will also look at how these are calculated and using intuition how to understand and recognize whether a signal is an energy signal or a power signal and the related consequences. These are the topics for today's lecture. So let's start by looking at how to represent discrete time signals. As we know that once the signal is sampled, then the independent variable becomes small n, which is the integer sequence coming from minus infinity to 0 and going to infinity. So one of the ways to represent any discrete time signal is the functional representation. So for example, if we say xn is equal to cos 2 pi 1 over 4n, then this is a mathematical representation of a discrete time signal, and this is typically called functional representation. Similarly, if in this example we can see that xn has some values. The value of xn is 1 for n equals to 1 and 3, and xn equals to 4 for n equals to 2, and for all other values of n, the value of xn is 0. So this is one way of representing a discrete time signal. Another way to represent a discrete time signal can be to expand this representation in a tabular format, where you can have n as 0, minus 1, minus 2, minus 3, and so on. And on the right it's 1, 2, 3, 4, 5, and under these number of n, you write the signal values. So as we saw earlier, that value of xn for n equals to 1 and 3 was 1, and for n equals to 2 it was 4, and for all other values of n, the value of xn was 0. So this is another way, not very common, but this is another way of representing a discrete time representation. The third way of representing a discrete time signal, which is more common, and we will be repeatedly seeing this representation, is sequence representation, where we use the curly brackets to represent the signal values there. So all of these values dot 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 0 0 1 4 1 0 0 etc. These are the signal values, and in order to indicate where is the origin, time origin, which is n equals to 0, we place a small vertical arrow under the value of the signal where n is equal to 0. So in this example, where xn was 1 for n equals to 1 and n equals to 3, and it was 4 for n equals to 2, n equals to 0 lies just one sample before the first one. So this is a common way of representing a discrete time signal, and these dots represent that on the left and on the right these zeros are continuing, and this represents an infinite duration signal. Whereas if a signal is bounded either on one side or another side, so we represent it in this form. So you can see that 0, and before that it's there are no dots
representing the signal is going in the negative direction. So this is bounded from this side, and from this side it is dots are showing that this is continuing as 0 0 0 and so on. So this is another way of representing uh, a discrete time signal. And obviously there is another way to represent a signal, which is the graphical format. And as in difference to the continuous time signal, where we typically plot the signal in the continuous format, the discrete time signal representation in graphical format is represented by these stem values. And if you are going to plot the signal using MATLAB, then the usual command for plotting this type of diagram is to use stem instead of plot. So these are some of the representation styles which are used for the discrete time signals. So now this is